Today we are going to design a combined footing. At first, let's see the preview of this tutorial. Here I have made a 3D model so that you can easily understand the design of the combined footing. We are going to follow the step-by-step process to design the combined footing. At first, we will determine the required area and length and width of our footing base. Then we will draw the shear force and bending moment diagram. Then we will determine the effective depth and check the punching and flexural shear resistance. Then we will calculate the required steel area for our footing base. We will design the top, bottom and transverse reinforcement for the footing base. And finally we will draw our complete design. So make sure you watch the full video. Here a combined footing which is supporting one exterior and one interior column. The exterior column is 18 by 24 inch and the interior column is 24 by 24 inch. And the center to center distance between these two columns is 18 feet. Here the dead load and live load for both the interior and exterior column is given here. The compressive strength of concrete and the yield strength of steel is given, and the allowable bearing pressure of soil is given, which is 6,000 pound per square feet. Here the footing base is 6 feet below from the ground level. Our first step is to determine the required area and length and width of the footing. If I remove this two column, then we can clearly see the footing base. This will be the length and this will be the width of the footing. Here, if we divide the total loads by the effective soil pressure, we will find the required area of the footing base. To find the effective soil pressure, we have to deduct the self weight from the allowable soil pressure. At first, we have to determine the average unit weight, which is the average unit weight of soil and concrete, which is 125 pound per cubic feet. And you know the footing base is 6 feet below from the ground level. Here also a surcharge load is given, which is 100 psf. So in your question, if there is no surcharge, you don't have to add this value. So after calculation, we find that the effective allowable bearing pressure is 5150 pound per square feet. Here for the exterior column, the dead load and live load was 170 and 130, and for the exterior column the dead load and live load was 200 and 250 respectively, and we determined the effective allowable bearing pressure is 5150 psf, and we'll multiply the loads with 1000 to convert them pound to kip. Now after calculation, we find that the required area is 145.63 square feet. Our next step is to determine the length and width of the footing. As our exterior column is along to the property line, so we cannot expand our footing base from here, but in the interior column we can expand our footing base. You must know that the resultant load, total load of these two columns is work at the center of the footing base. Suppose the distance of resultant force R is x feet from the center of exterior column. So if we find the length of the x, then if we multiply this with 2, then we'll find the total length of the footing base. Here the resultant force R is the summation of the loads which is applied in the two columns, which is 750 kip. Then if we calculate the moment according to this point, for P1 will be P1 into 0, as the distance is 0 here, and for P2 the distance will be 18 feet. This two moment will be equal to the resultant moment, which is R into x. So here we'll find the x is equal to 10.8 feet. As the center from this column to the center of the footing is 10.8 feet, if we add the other half of the column and then multiply this with 2, we'll find the total length of the footing, which is 23.1 feet. So for workability, we should design that the length is 23.25 feet. Now as we know the required area and the length, as we divide the required area by the length, we can easily find the width of the footing, which is 6.26. For better workability, we should take 6.5 feet. Our next step is to determine the net upward soil pressure. You know that the allowable bearing pressure of the soil is given 6,000 pound per square feet, but we have to increase this as we are doing the USD method. In this method we have to increase the dead load and live load with multiplying factor, so that as the load is increasing, the upward soil pressure will be increased. Here the dead load for both the two columns, which is 170 and 250, we will multiply this 1.2, and for live load we will multiply the loads with 1.6. Then we will divide the loads with the area. In the previous step we found that the length and width is 23.25 and width is 6.5. So footing area is 23.25 into 6.5. Now after calculation we found that upward soil pressure is 6.83 kip per feet square. Now if we multiply this pressure with the width, which is 6.5 feet, we'll find the net upward soil pressure in the longitudinal direction, which is 44.4 kip per feet. In this step we are going to draw the shear force diagram and bending moment diagram for the calculation of the reinforcement. I have created some sections for better understanding and for easy calculation. At first let's draw the shear force diagram. At this point the force is 0, and at this point let's see which loads are working here. Here you can see that I have multiplied the column dead load with 1.2 and the column live load with 1.6. So the total load is 412 kip. This is a point load, and through this section the UDL is 44.4 kip per feet. So if we wanted to determine the load in this section, at first this is the upward direction, so we are taking this as positive, and this point load is the downward direction, we are taking this as negative. And for this point the total upward load is 44.4 into 18 by 12, as this is 18 inch, and by dividing the 12 we are converting this to inch to feet, and then we deduct the downward point load, which is 412 kip. Then we find that the load is minus 345 kip. So this will be the load at this point, as this is minus, so we'll draw this at downward. So we'll connect this 2 point, and then let's see that here is a section at this point, and between these two sections there is no point load, only the upward load is working. So if we multiply the upward load with the distance between these two sections, we'll find the load in this section. To find the clear distance of this two column, we have to deduct the half distance of this two column from the center to center distance. So here we find that the clear distance is 16.25 feet, which is the distance between these two sections. Now our previous load was minus 345. Then we'll add the UDL load in between these two sections, which is 44.4 into the distance is 16.25. Then we find the load is 376 kip. So at this point the load will be 376, so we'll connect these 2 points. Now we have to calculate the load at this point. Now let's see that there is a point load and some UDL load is working in between these two sections. The point load is 620 kip and the UDL load will be 44.4 into the distance between these two sections, which is 2 feet. Our previous load was 376. We'll deduct the point load, as this is the downward load, and we'll add the upward load, which is 44.4 into 2 feet. Then we find that the load is minus 155 kip. So we'll join these 2 points. As you know that the load at the end point will be 0, so you can easily connect this with the end point. Now let's draw the bending moment diagram. At first, for this section, if we apply the triangle equation, which is half into base into height, so here 0.5 into the base is 18 inch and the height is 345 kip, so the moment is 3105 kip inch. Now here at this point the shear force is 0. We might find the maximum bending moment at this point. So at first we have to determine the bending moment at this point. To do that, we have to calculate the distance of this section. Now as at this point the shear force is 0, here the upward load is 44.4 into the distance, which is x, minus the downward point load, which is 412. So we'll find the value of x, which is 9.28 feet. Now we have to determine the moment at x distance. We'll apply the triangle equation for this full section, which is 0.5 into the base is 9.28 feet and the height is 345 kip, and we'll multiply this with 12 as to convert this feet with inch. So after calculating, we find that the moment is 19,230 kip inch. Now we have to calculate the moment for this cantilever portion. We know that the moment equation for the cantilever portion is WL square by 2. Here the W, which is the UDL, is 44.4 and the length is 3.5 feet. We'll multiply the value with 12 to convert this from feet to inch. Now we find in this point the moment is 3255 kip inch. Now we have to check the flexural shear resistance of our footing base. The critical section for the flexural shear failure is D distance from the face of the interior column. So we have to calculate the shear force at this point. We know that the shear force at this point is 376 kip. So if we deduct the upward load of this portion, we'll find the shear force at this point. The upward load for this portion is 44.4 into this distance, which is D. At first we have to assume the effective depth. Here D is the effective depth. You know the effective depth is the distance from the top of the footing base to the center to center distance of the reinforcement. So now at first we have to assume the effective depth. Let's just say that the effective depth is 37.5 inch. If we put this value in this equation, we will find that the shear load at this point is 237.25 kip. Now we will check the design shear strength of concrete. That means how much loads that our concrete can be resisted. For this, the equation is phi into 2 root over f prime c into bd. Here b is the width of the footing base, which is 6.5 feet, and phi for the shear strength is 0.75, and d we assumed 37. We find that the strength is 240.31 kip. That means the concrete can resist 240.31 kip, which is bigger than the flexural shear at this point. So our assumed effective depth, which is 37.5 inch, is okay. If you have trouble to assuming the effective depth value, you can use an alternative method. Here, at least the flexural shear have to be less than or equals to the design shear strength of concrete. If we use these two equations here and solve this with calculator, you can easily find the effective depth value here, which is 37.2, and approximately we can use 37.5 inch. In this step, we are going to check the punching shear. For combined footing, the critical section for the punching shear is d by 2 distance from the face of the exterior column. As you can see, at this portion is the critical for the punching shear. So we have to calculate the area of this portion. The length is 2 feet and both the side is d by 2. So we should add d, which is 37.5, and the width is 18 inch plus half of the effective depth. 18 plus half of the effective depth, and you can see that we find that the area of this portion is 15.69 feet square. Now we have to calculate the perimeter of this portion. Here the perimeter will be the summation of these three faces. We will not include this face. We know this two length from our previous equation. Let's just put this two length here and multiply the width with 2 to find the length of these two faces. And after calculation, we find the perimeter is 11.25 feet. Now we have to calculate the shear at this section. To find the punching shear at this section, we have to deduct the upward soil pressure from the point load. The point load at this column was 412 kip, and the upward soil pressure is 6.83 kip per feet square, and the area we found 15.69 square feet. After calculation, we find that the punching shear at this section is 305 kip. Now let's see the design concrete shear. Here the design concrete shear equation is phi 4 root over f prime c into b naught into d. B naught is the perimeter we find, which was 11.25, and the D is the effective depth, and after calculation we find that the load is 831.85 kip, which is greater than the punching shear. So our assuming effective depth is okay. So now the total thickness of the footing will be the effective depth plus 3.5 inch. We assume that the left distance of the thickness is 3.5 inch. So we add this value with the effective depth. So we find that the thickness is 41 inch. Our next step is to determine the required steel area for our footing base. For this we need our shear force and bending moment diagrams. At first, let's see what kind of reinforcement we are providing. If we hide the concrete, we can clearly see the reinforcement of this footing. Here you can see that there is a top reinforcement and bottom reinforcement and transverse reinforcement for both the column. The top reinforcement is provided for the negative bending moment and the bottom reinforcement is provided for the positive bending moment. Now let's start the calculation of the required reinforcement. In the USD method, to determine the moment, the equation is phi into AS into Fy into D minus A by 2. S is the required steel area, and for concrete, tension equals to the compression. The tension equation is S Fy and the compression equation is 0.85 into F prime C into AB. From this equation we find that the A is equals to AS into Fy by 0.85 F prime C into B. Here we do not know the reinforcement steel area, so by putting the other values we find that the A is equals to 0.3 into steel area. Now for the top reinforcement, here you can see from this equation we find that the steel area will be M divided by phi Fy into D minus A by 2. Now that we know the moment, at first we are going to determine the top reinforcement. As I said before, that we provide the top reinforcement to resist the negative bending moment. Here the maximum negative bending moment is 19,230 kip, so we are taking this as our moment value. And for reinforcement calculation, the phi value is 0.9 and the yield strength of steel is provided 60 ksi, and the effective depth is 37.5, and we calculated that the A is 0.3 AS. After calculating, we find that the required steel area for the top reinforcement is 9.88 square inch. So if we use the number 9 bar for the top reinforcement, the area of each number 9 bar is 1 inch square, so we'll need approximately 10 number 9 bar for our top reinforcement. Now we have to calculate the bottom reinforcement. To resist the positive moment, we have to provide the bottom reinforcement. Here the moment is 3255 kip inch. If we use this process to determine the bottom reinforcement, we will find a smaller value than the required minimum steel area. That there are two equations for the minimum steel area, which is 3 root over F prime C by Fy into BD and 200 by Fy into BD. We'll take the bigger value from these two equations. Here B is the width, which is 6.5 feet, and D is the effective depth, 37.5, and we find minimum steel area is 8.01 square inch, and in other equation the minimum steel area is 9.75 square inch. So as this is bigger, so the minimum steel area will be 9.75 square inch. So if we use the previous method as we use for the top reinforcement, we will find that the steel area will be less than and that the 9.75 square inch. So we should use the minimum steel area as the bottom reinforcement, which is 9.75 square inch. Now if we use number 7, the steel area for number 7 bar is 0.6 square inch. So now if we divide the steel area by the bar area, we'll find that we need 17 number 7 bar in the bottom. And now we have to design the transverse reinforcement for both the two columns. At first, let's design for the interior column. For interior column, we have to provide transverse reinforcement up to D by 2 distance from the both face of the column. At first, calculate the width of this portion. Here that this distance is 24 inch plus both the sides have D by 2 distance, so we'll multiply the D by 2 with 2. We'll find the width of this portion, which is 61.5 inch. As you know that the point load at this interior column is 620 kip, so if we divide the load with 6.5 feet, which is the width of the footing base, we'll find the net upward load per linear feet, which will work perpendicular to the width. At this section we have to calculate the moment, so we can just use WL square by 2 equation for determining the moment at this section. Here the unit load W is 95.4 kg per feet and the length is 2.25 feet, and we find that the moment is 2900 kip-inch. If we see the 3D model, you can see that the transverse reinforcement bars are placed on top of the bottom reinforcement, so here the effective depth will be reduced. So we will deduct 1 inch from the effective depth to find the actual effective depth for the transverse direction. This is kind of similar to the previous step. If we use the method as we used to determine the top reinforcement, we'll find that the steel area is 1.48 square inch. Then we calculate the minimum steel area, which is 7.48 inch square. So you can see that the minimum steel area is greater than the actual steel area, so we have to use the minimum steel area as the transverse reinforcement for this interior column. So if we use the number 7 bar, which area is 0.6 inches square, we will need 13 bar at the transverse direction for the interior column. Now we have to calculate the transverse reinforcement for the exterior column. We have to provide the transverse reinforcement up to the d/2 distance from the face of the exterior column. At first calculate the width of this portion, which is 18 inch plus d/2, which is 36.75 inch. Again, as the previous step, we have to calculate the net upward load per linear feet. As you know that the point load at this column is 412 kip. If we divide this by the 6.5, which is the width of the base of the footing, we'll find that the net upward load per linear feet is 63.38 kip per feet. Then we have to calculate the moment at this edge of this interior column. We can use the equation WL square by 2, and from this we can determine the steel area. The actual effective depth will also be reduced like the interior column, which is 36.5 inch. This is same as the interior column, that if you use this equation to find out the steel area, you will see that this steel area will be lower than the minimum steel area, so we have to use the minimum steel area. Here B is the width of this portion, which is 36.75. D is the actual effective depth. Here we find that the minimum steel area is 4.47 square inch, so the steel area in the transverse direction for the exterior column will be 4.47 square inch. If we use number 7 bar, which area is 0.6 square inch, we need 8 number 7 bar for this transverse direction for this exterior column. Here you can see that this is our final design. This is the top view and this is a section cut view. In this top view we can see that the length of our footing base is 23.25 feet and the width is 6.5 feet. And in the section cut view we can see the reinforcement distribution. Here you can see in the top reinforcement we have provided 10 number 5 bar, in the bottom reinforcement 17 number 7 bar, and in the transverse direction of the exterior column we provided 8 number 7 bar, and for the interior column 13 number 7 bar. Thank you for watching the video. If you can learn something, please like the video and subscribe to my channel. And I have a question for you. Do you know when we design combined footing instead of isolated column footing? If you know the answer, comment below, and if you don't, you can ask me, I will reply.